Hello there. Today I will show you how we use processing Modflow to simulate transit groundwater modeling. In previous tutorial 1, I show you steady-state groundwater modeling, and I hope you understand how to simulate steady-state groundwater flow modeling. I start to this tutorial, and this tutorial 2 I'll show you which additional input data is needed for transit groundwater modeling, and how to build and run a transient groundwater model using processing Modflow. For a transit groundwater model, some additional inputs data are needed compared to a steady-state groundwater model. These are initial hydraulic age, time parameters, and storage parameter value. Of course, in a steady-state groundwater flow simulation, we use initial hydraulic head, but initial hydraulic head that we use there is prescribed hydraulic, which is we can guess that's a value, but in this case we have to use the initial hydraulic head, which is simulated using steady state. Problem formulation given for us an unconfined aquifer. You can look at this figure. This one is the figure of the aquifer. Is a coarse-grained sand with a measured isotropic hydraulic conductivity of 160 meters per day. Here, hydraulic property of aquifer is isotropic, and that value is 160 meters per day. Specific yield and effective porosity have been assessed for the aquifer, and the value is 0.06 for both specific yield and effective porosity. Recharge to the aquifer only occurs throughout 4 months in rainy season, and this parameter is time dependent parameter, so it's vary with season. During rainy season there is recharge, and during dry season there is no recharge, and this recharge value is 7.5 times 10 raised to minus 4 meter per day. Outside of the wet season there is no recharge to the aquifers. The elevation of the aquifers, top and the bottom, are given for us, and the top elevation is 25 meter, and the bottom elevation is the datum, which is 0 meter respectively. So the thickness of the model will be 25 meter. The area of interest is also given for us here, which is 10,000 by 6,000 meters, and this aquifer is bounded by no flow zone to the east and west. This boundary is no flow boundary, and this boundary is no flow boundary. That means whether geological formation here at the boundary does not allow flow of water out of the aquifer or into the aquifer. That means water do not flow from this boundary to the aquifers, or from aquifer to geological formation out of the aquifers. The same is true for west boundary also. And there is also a volcanic mountain in the southeast corner of the model, and this one is southeast corner of the model, and this southeast corner of the model having geological formation, impermeable geological formation, so there is no flow of water in this geological formation, and that was considered as what? Aquifers. And the not allow flow of water out of aquifers or into aquifers via this geological formation. To the north, an area of constant hydraulic head exists with the value of 1.5 meter. If we see this one is constant. This boundary is constant head boundary. That means geological formation at this north boundary is fully hydraulic contact with the aquifer, so water flow out of the aquifer to the river, or from the river, or from water body to the aquifers in this boundary. The southern boundary is specified flux boundary with inflow rates of this value 0.0672 meter cube per day per meter. So here we have a specified flux boundary, and this amount of water is flow to the aquifer 0.0672 meter cube per day per meter. Amount of water is flow to the aquifers via this boundary, south boundary. Total of 9 wells in the area are pumped at a rate of 45 liter per second, which is equivalent to 3,888 meter cube per day, each during 8 months dry season. And this one is another time dependent variable, and this discharging or pumping of water from the aquifer is only during dry season. And our task is to assess the water level in the aquifer, and this water level in the aquifer is determined by time dependent variable. Those time dependent variables are what? Recharge, which is only during wet season, and pumping, which occur during dry season. So we are going to evaluate the effect of those time dependent variable on the water level in the aquifers or hydraulic head of the aquifers. Okay, before starting modeling or simulating groundwater flow, first we have to have conceptual model, and conceptual model choice are made like this. First, you have to know whether the simulation will be steady states or transit. We have some time dependent variables, so transit model are in it since time dependent stress factors are present. Time dependent stress factors are what? Recharge, which is during wet season, and discharge or pumping, which is what? During dry season. And period one within the length of what? 240 days, which is dry season. There is what? Pumping during this season. And we can use a different time step while simulating transit model. For current tutorial, I use 12 time step of 20 days for period 1 and 6 time step of 20 days for period 2. Initial head of transit model need to be calculated using steady states, so we have to simulate first steady state before simulating transient model. One aquifer, we have one aquifer, and that aquifer is unconfined aquifer. You can read here from conceptual, from problem formulation, an unconfined aquifer. So we have only one aquifer, and that aquifer is unconfined aquifers. Model dimension is also given for us, so this model dimension is correspond to the natural boundary of the aquifer, which is given in the problem formulation. So we have to use this model dimension, which is 10,000 by 6,000 meter, correspond to the natural boundary of the aquifer. Model thickness of 25 meter correspond to the aquifer thickness will be used. Grid cell with variable size. We use variable size of grid cell because we have pumping well, and near to this pumping well, the hydraulic gradient is high. And now the gradients to evaluate that high hydraulic gradient, we have to use small size of grid, and by far from this well, the hydraulic gradients may be small, so we have to use different types of grid cell, and a grid cell with variable size, which is 167 meter around the wells to 500 near the boundary will be used. Parameters like hydraulic conductivity, porosity are given for us, so we use those parameters. And also boundary condition need to be conceptualized. No flow boundary at east and west boundary. We have no flow boundary here at east and west boundary. A fixed head boundary at the north boundary, because we have here fixed height. We have fixed head, and so this aquifer is fully hydraulic contact with what water body adjacent to the aquifer. No flow boundary at the bottom of the model will be used. We assume that the bottom of the aquifer is what basement geological formation, which is impermanent geological formation, assuming no flow boundary at the bottom of the model. Constant recharge boundary at the model top will be used because we have what recharge to the aquifer from the top. That's a recharge could be from precipitation. Well, before starting simulating transient model, first we have to simulate steady states model. First, steady states model is built to serve as initial condition for what transient model. Let us start our simulation. First, we have to create a new model of processing Modflow. To create a new model of processing Modflow, we have to click here, File, then New Model. Then we'll navigate to the folder where we need to save our model. Let us create a new folder, tutorial 2, and let us name the model as tutorial 2. Save. So we already create our new processing Modflow, and then the next procedure is what? Assign mesh size of our model, or grid size of the model, and to do that we have to click here on grid, then mesh size, click on mesh size. Okay, well, model grid and the coordinate system will appear here. This model grid, and this refers to the coordinate system. Let us look at the model grid. Number of layers, we have only one layer, which is unconfined aquifer. Model thickness is 25, and the model top elevation is 25. And here the number of column and the model extension need to be assigned. Model extends the dimension of model row is 10,000, and the number of row can be vary from this value. Actually, for the time being, I use this value. And model extends to the column dimension is 6,000, and let us do this one first. We can change this vertical exaggeration, and this vertical exaggeration needs to exaggerate the vertical difference of what the model made while determining hydraulic gradients. Then, okay. So here grid size is created. Let's say actually for this tutorial we have a basement base map, so it's better to load that base map from the folder where it's saved. Click on option, then model, then click this one, then right click here and navigate to the folder where the data is saved or base map is saved. Example and tutorial 2 base map, then okay, then okay. So here base map is what loaded to our model. Then click here leave editor, then processing Modflow asks us to save change to the mesh size. Yeah, accept it, yes. Then click here again, then mesh size. Here in conceptual model we say that we will use different grid cell size, which is 500 meter near to the boundary and 157 meter around the well. So the size of the cell near to the well should be small. To do that, click on this cell, and then control on the keyboard, then up arrow. So 2 line is added to the cell. Do the same thing for another, then the cell size will be reduced to the value in it. Once you finished this activity, click here on leave editor, then pressing Modflow asks you to save change to the mesh size. So you have to accept this request and say yes. And here processing Modflow asks you to save backup copy of your model, but it is not in it to save our backup copy of our model, and ignore this one and say no. Yeah, and now we already assign mesh size for our model, and the next procedure is assigning layer property. To assign layer property, click on layer property, then this window will pop up, and here there are different types of layer property: confined, unconfined, confined and confined, confined and confined with transmittivity vary and constant. Our aquifer is what unconfined aquifer, so you have to click here on unconfined, then say OK, and you have to confirm this one from conceptual model and the problem formulation. The aquifer is what unconfined, it is only one layer. Then the next is what assign cell status. To assign cell status, click on grid, then cell status, then I want Modflow, and here the cell status of our model is observed here. If you click everywhere in the model, you can see the cell status is 1. That 1 refers to active cells. So all cells are what active cell, but in our case, some cells are inactive cell and some cells are constant head cell. For instance, all cells at the north boundary should be assigned as what constant the head cell. To assign that one, click here on this cell, right click and change this value to -1. Change this value to -1. So this cell is assigned to be cell having constant head. We have to do the same for all cells in the north boundary. To do that, click here on cell by cell duplication, then duplicate this value to all cells at what north boundary. Then uncheck this cell by cell duplication, and some cell here from conceptual model choice, you can see here there what some volcanic mountain in the south corner of the southeast corner of the model, and you can see the same thing here also. This geological formation here in southeastern boundary are what volcanic rock, and this volcanic rock are impermeable geological formation. They does not allow flow of water, so we have to assign cell in this area as what no flow cell. To assign that what, click here on one cell, click like this and right click, then assign this cell status to 0. 0 means there is no flow. Then okay, duplicate this cell value to all cells having the same property, and click this cell by cell duplication and duplicate this value to the cell having the same property. Okay, now cell status is assigned to each cell of the model. So leave this editor, then yes. Next procedure is what? Assigning top layer property and bottom layer property. From conceptual model choice, we have the property that the model thickness is 25, correspond to the aquifer thickness, and you can see here the elevation of aquifer top and the bottom are what? 25 and 0 respectively. So you have to assign this property to the model. Top layer property, then click value, reset. Actually the value assigned here is 25, which is the same to the elevation layer top. Accept it, then leave editor, yes. Grid, bottom elevation, value, reset matrix. The elevation of the top, the elevation of layer bottom is 0, so accept it as this, then leave editor, then yes. So we already assigned mesh size, layer properties, cell status, top and bottom layer properties. The next procedure is what? Assign some parameter of the aquifers. One of the parameters need to be assigned here is what? Time property. We have to click on time, and simulation time units needs to be the same to the unit that used in problem formulations, or the, for example, here we use hydraulic conductivity of the aquifer is 160 meter per day, so here the unit is day, and here also it is day, here also it is day, so we have to change our simulation unit to day. So click here, then day. So simulation time unit is what? Day, and simulation type is what? Steady state flow simulation. Then okay. Then we have to assign initial and prescribed hydraulic property. Let us assign initial and prescribed hydraulic property to each cell, reset. Then let us make this value 60. Actually, this one is just default value. Okay, and we have hydraulic head value for north boundary. To assign that value to north boundary, click on this cell, then right click, then assign this value as 1,5 and duplicate this value to all cell in the north boundary. To do that, click on cell by cell duplication and duplicate this value to all cell in north boundary, then leave editor, then yes. Next parameter is horizontal hydroconductivity. To assign horizontal hydroconductivity, click here on value, reset matrix. Horizontal hydroconductivity is 160 meter per day, then okay, then leave editor, then yes. Another parameter needs to be assigned. Effective porosity is also given for us. Value, reset matrix. Effective porosity of aquifer is what? 0.06. Then okay, then leave editor, yes. And other parameter given for us is what? Recharge and specified flux value. So to input those data, click on model, then Modflow flow simulation, flow package. We do not have drain package, we do not have evapotranspiration package, we do not have general head boundary, horizontal flow boundary, but we have recharge data. So click on this value on this package, recharge, then assign the value given here. That value is value. You have this value 2.5 times 10 to the power of minus 4 meter per day for steady state simulation. So value reset matrix 2.5 10 to the power of minus 4. Then okay, then click yes. Another parameter we have is another parameter here we have is specified flux boundary, and that specified flux boundary is 0.0672 meter cube per day per meter. So we have to assign that value to the model. To do that, model, then we use well package, and click here this cell and right click. So in this case aquifer is gaining, so there is constant flux, specified flux to the aquifer via this boundary, and that flux is equal to this value per meter, and the cell size of this grid is what? 500 by 500. So to get this value we have to multiply this value, by 500 meter, and the value will be equal to 33.6. So we have to assign this value, which is 33.6. Then okay, this let us duplicate this value to this cell also. However, the value for the next cell, this cell is half of this one, because the cell size of the width of this size, this cell is what? Half of this cell. So click on this one, right click, then half of 33.6 is what? 16.8. Then okay, then let us duplicate this value for this one. Okay, and the size of this cell is what? 1/3 of this cell, 1/3 of this cell. So right click on this one, 1/3 of 33.8 is equal to 11.2. Then okay, then duplicate this value to entire cell in the source boundary, then leave editor, then yes. Now we already input all parameters to the model for steady state flow simulation, so we can run our model by clicking here on model, then flow simulation, then run. Then okay. Now we can observe our T2D visualization. Using the 2D visualization, we can observe hydraulic distribution of steady state flow simulation. But our concern is not to simulate steady state flow simulation. Our concern is to simulate transients, and we run steady states to use as initial inputs for what? Transients. So leave this one, and to simulate transient flow simulation, click on here on parameter time. In this case, we have two period. We have two period, dry period and wet period. The length of what dry period is? The length of dry period is 240 days, and the length of wet period is 120 days, and the time step of period 1 is 12, and the time step of period 2 is 6. And you can see that from here, from conceptual model choice. Conceptual model time step is 12 for period 1 and 6 for period 2. And simulation time unit is day, and simulation type will be transient flow simulation. So change to transient flow simulation, then okay. Another parameter, specified yield, is also given for us, then value, then reset matrix, specific yield value 0.06, then okay, then leave editor, then yes. Another parameter given for us here is what? Time dependent variable. Those time dependent variable are what? Recharge and pumping. Let us input those parameters. Click on recharge, then edit. Here we are in what? Period 1. Period 1 refers to dry period, and in this dry period, there is what? No recharge. So the recharge value will be 0. So click on value, then reset, and make the value of recharge equal to 0. To get period 2, now we are in period 1. To get to period 2, click here on change stress period, then click this one, then edit data. Now we are in what? Period 2. So we can use this recharge package in period 2, and in period 2 there is recharge because this period is rainy season, and we have to set this value value, reset matrix, recharge value is 7.5, 10 the power of minus 4. Then okay, then leave editor. Yes, another data we have is what? Pumping. So you can use well package. Click here on well package, well edit. Then here we are in period 1, and this period is dry period, and during dry period there is pumping activity. Water is what? There is pumping activity. You can see here in problem formulation, a total of 9 wells in area are what? Pumped at this rate, each during what? This dry season, to supply water for what? Irrigation and domestic purpose. So we have to use this value for each well. Click on the cell where the well is located and right click and give the value, and that value is what? 3888. And in this case we have to use negative value because aquifer is losing water. Water is what? There is abstraction of water or pumping of water from the aquifer, so aquifer is losing water. So use this value. Then okay, do the same thing for all well. Right click, minus 3888. Okay, well 3. Okay, 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 well 8, well 9. I made a mistake here, so I have to correct it. Now we assign pumping rate data for each well for period 1. We have to do the same thing for period 2, but the pumping values 0 during rainy season or during period 2. That's change stress period. Then period 2 edit data. So we have to assign this value to 0. There. Zero. 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 Then okay. Then leave editor. Yes. Well, we already input all parameters that we have. Then we can run Transient groundwater flow simulation. So click on model, then flow simulation, then run the model. Then okay. Yeah, the model already finished running, and here press any key to continue on the keyboard. Then we can visualize our results. Let us visualize 2D visualization to visualize our result. 2D visualization. Let us visualize hydraulic head distribution. Then okay, and this one is hydraulic head distribution, and here we have different period and different time step. So the hydraulic head distribution in different period and different time step are not the same. It's not the same. If you change the period and the time step, then you can see change in what's head distribution in the model. Let us see the animation of head distribution that change due to the activity of pumping and recharge. Click on animation, then let us navigate to where we need to save our outputs. Then let us say head distribution, then open, and let us change this display time to second, then okay. So you can see here the head distribution change, time milli, or head distribution change after each 20 days in the aquifer due to what? Due to time dependent variables. In this case we have two time dependent variable. Recharge is one of time dependent variable, and pumping is another time dependent variable. What we understand from this head distribution is while we pumping water from the aquifer, the amount of water that pumped or abstracted from the aquifer should be not greater than what? The amount of water that recharged to the aquifer during what? Rainy season, and that is what we need to consider while constructing pumping well in each aquifer to control depletion of what ground.